Right now we're going to solve a particle kinematics problem. We've got a particle which is initially located at the origin, and the information we have here says that it moves along a straight line through a fluid such that its velocity is given by the equation shown. Our goal here is to determine the displacement of the particle during the first 3 seconds of its motion. Let's start by drawing a picture here to make sure that we can properly visualize what's going on. So let's see if we can draw a particle over here. Maybe somehow like that. And then we're told that it starts at the origin. So that suggests that we could define a coordinate system. And since we know that we have a straight line motion through a fluid medium, it makes sense to just go ahead and use the motion direction as one of the coordinate directions. So in order to visualize this, I'll put an x-axis over here, let's say. Maybe a y-axis up here. And I am going to visualize this particle moving here in the x direction. And it's going to move in a way where the velocity is given by an equation that looks like this. It's an exponential, and I'll point out here that this is given units of meters per second, but we're also defining our equation here in terms of time. So it's not a position coordinate, it's not like a function of x, it's a function of time here. So we're going to have to think a little bit about how to get at the information that we want to get to. Okay, so let's think about what an approach is going to be. So step one is something that we've actually already implicitly done, but it's a good habit to get into, and that is to consider the coordinate system. Okay. Now, the problem statement certainly suggested a coordinate system that makes sense, but in many cases you might have some more flexibility, and it's a good thing to insert this as step one in your approach. Now, the way this is going to work out is that we're really going to be able to express this as a position integral. So we know an equation for the velocity, and we know that position is somehow going to be some sort of integral of that equation. And the question is, what are the bounds of integration and how do we do the integral? Well, that's what we're going to do in step two. So we'll set up this position integral and make sure that we answer all of those questions in step two. Okay, so let's go ahead and do step one right here on this page. So step one is to define a coordinate system. So as I said, the problem statement clearly suggested a kind of coordinate system that we could use. We know that the velocity here is an explicit function of time, and that we're dealing with units of meters per second. Okay, so we sort of already completed this part. Again, any problem that you come up with, you might have more flexibility about how you define the coordinate system, so it's important to put step one in there so that you have a chance to reflect on what would be the most appropriate coordinate system for any given problem. Okay, that being said, let's go ahead and start step number two. So step two is to do a position integral. And perhaps the big question is, what is the form of that integral? What is it going to look like? So we're going to define a position coordinate in the x direction, and I'm going to call that coordinate s, and that's consistent with the notation in the book. And we know that s is related to v by a simple differential equation, so v is equal to the derivative of s with respect to t, and that means we can sort of separate that and we can write an equation which looks like this. So we've separated out the ds and the dt part, and what we're going to do here clearly is we're going to make these things into integrals, and that's going to be our position integral, as you shall see. Okay, so since our path seems clear now, we know that we can write an equation that looks like this. So ds, an integral, is going to be an integral of v dt, and that's going to look like this. So it's 1.8 1 minus e to the minus 0.3 t dt. Okay, so there is our equation that we were given. Now I've left the bounds of integration blank for the moment because we need to talk just a little bit about exactly how to do this. Okay, so the bounds of integration are going to look like this. In the problem statement, we are told that we're looking for t to be from 0 to 3. Okay, so we want to capture all of the motion across that time scale. And so what that means is that if we can express the left side of the equation above that, here, this ds, this will just be, that integral will just represent the change in position delta s. That's what we're looking for. And then if we want to integrate over t, now we know we're going to integrate over the interval 0 to 3. And so that is the way our integral is going to look. Okay, so now it's just a simple matter of going ahead and doing the integral and seeing what we get. So let's go ahead and do that. So we know that delta s now is going to be this integral from 0 to 3 of 1.8, 1 minus e to the minus 0.3 t dt, and we're going to be able to break this up in a couple of ways. So for example, here we're going to do 1.8 out in front, and then brackets we'll do an integral from 0 to 3 of 1 dt minus an integral from 0 to 3 of e to the minus 0.3 t dt, and we'll close that bracket. Now this first integral, you can see clearly this one is just going to be equal to 3. That's an easy one to do. Now the question is, what about this integral right here? There's a little bit of work to do there, and we're going to do that work on the next page. Let me stick with the red color here, and let's just focus on that one piece of the integral. So an integral from 0 to 3 of e to the minus 0.3 t dt. If you recall from your calculus class how to integrate this, we get this kind of an expression, 1 over minus 0.3 e to the minus 0.3 t, and we're going to evaluate that from 3 to 0. And so this then becomes minus 1 over 0.3 e to the minus 0.9, that's 0.3 times t is equal to 3, and then from that we're just going to subtract 1, and let me remind you that that 1, that's really just e to the 0. Okay, so if we do all that and we substitute it back into the original equation for delta s, we get delta s is equal to 1.8 times the bracket, it's 3 minus 1 over 0.3 times e to the minus 0.9 minus 1, there's the square bracket, and if we start doing the calculation, we can figure out that this term right here, this is about equal to 1.98. And so if we carry through the math to the next page, here's what we get. We get delta s is equal to 1.8, 3 minus 1.98, and this just ends up being delta s is equal to 1.84 meters, and that's from time equals 0 to time equals to 3 seconds. And there is your solution. Let's go ahead and review what we did. So the problem statement told us that we had a particle that was moving in a straight line according to a given equation. That equation was a function of time, and we were trying to figure out the displacement of that particle during the first 3 seconds of motion. So the first thing we did was consider a coordinate system, and in this case it was pretty straightforward to do. In the general case it might not be. You might have more flexibility with how you define the coordinate system. So here it just so happens that the first step was pretty straightforward. Step 2, however, defining the position integral, was a little bit more involved. The key here was the equation which related the velocity to the position coordinate s. But once we set out to do the integral, we could define the integral in terms of the velocity equation, go ahead and do the integral, and once we made our way through all the math, we ended up with the solution. Delta s is equal to 1.84 meters. In this problem, we're going to be looking at the rectilinear kinematics of a particle. So we've got a particle that is moving through an electric field from one plate to another. And the velocity profile of this particle has the shape shown in the figure. We're given some information about Vmax and the time scale in the figure, and our goal here is to draw the position and time graph and the acceleration versus time graph for the particle. Okay, so there's a couple ways to look at this. And we're going to start with a step 0, which involves making some observations and developing some expectations about what we're going to be able to see. But before we do that, let me just go ahead and write some things on the figure just for clarity. So we're told that our time scale here, t prime, is 0.2 seconds, which makes t prime over 2 0.1 seconds. We're also told that our Vmax here is equal to 10 meters per second. And it's not represented on this particular graph because this is a velocity versus time graph, but we're told that s equals to 0.5 meters at time is t prime over 2, which is 0.1 seconds. So when we draw our position versus time graph, the so-called ST graph, we're going to need to make sure that that information is captured on that graph. Okay, that being said, let's go ahead and write an approach about how we can solve this problem. So I'm going to insert a step 0 here, which is observations. Now you see this sort of step 0 frequently in these videos because there are many problems where it's very sort of straightforward to sit back and look at the problem statement and develop some expectations about how you think the problem is going to go. This gives you some intuition about how the calculations go, and it also gives you a point of sort of checking so that when you get an answer as a result of calculations, you compare it with your expectations, and that gives you some confidence that what you've done is correct. And we'll make those observations in a moment. We know that step 1 then is to consider the equation for Vt. We have a graphical version of it, but we don't have an equation which is written in terms of time t. And then once we have that equation, we're going to go ahead and derive an equation for s as a function of t. And from that equation, we are going to be able to draw the ST graph. The third thing we're going to do is we're going to take that velocity equation from step 1 and we're going to derive an equation for the acceleration as a function of time, and from that equation we are going to draw the AT graph. Okay, so we've got 4 steps here. The first one is an important one. It's observations. That's what we're going to do next. So step 0 here, observations. Now, off to the right here, I'm going to construct what I think the S, the V, and the A graphs are going to look like. So let me put up here a set of axes. Just sort of draw this off to the side here. So I'm going to start here. There's my time axis, and this is going to be acceleration. And then I'm going to put another time axis here. There's my velocity, and then another time axis up here. And that top axis is going to be my position. And then I'm going to put in 2 dashed lines to correspond to the relevant times. So let's say that's t prime, that's 0.2 seconds. And then over here in the middle, that's t prime over 2, that's just 0.1 seconds. Now in blue here, let me sort of draw in what we already know, and that's the information about v. So v is linear from 0 to 0.1. It's got a positive slope. And then it's linear again from 0.1 to 0.2, but it has a negative slope. Okay? So that's what we've got so far. Now the question is, how can we go about sort of figuring out what we think S and A are going to look like? Well, in order to do that, we can just write some basic equations that we know to be true. So for example, we know V is going to be ds dt, and we know A is going to be dv dt. So if V is linear, that implies that A is going to be constant. And it also implies that S is going to be somehow second order. Okay, it's going to have a second power dependence on time. And based on what we know about V, we can make some conclusions that look like this. So let me draw the speculative stuff in red. So if I go to the A graph over here, we know that the derivative of the V curve is going to be constant because V is linear, and we also know that since the slope of V is positive from 0 to 0.1 seconds, we know that A is going to have some constant, and it's going to be positive. And then by the same token, we can look at the velocity profile between point 1 and point 2, we recognize it's got a negative slope, and so we think that the acceleration is going to be down there somewhere. So you can see that there's going to be this sort of discontinuity in the acceleration as we go through time equals to 0.1 seconds. So that's our expectation on acceleration. It's kind of skew symmetric with respect to that center line at 0.1 seconds. Now, the S-curve is a little bit harder to visualize, and you may or may not be able to see this, but because of the nature of this, we know that there's going to be sort of an inflection point on S because V changes slope. We know there's an inflection point sort of here at point 1, and up to that point, the curvature is going to be concave up, and after that point, the curvature is going to be somehow concave down. So I didn't draw that exactly really smoothly like I wanted to, but you get the idea of what's going on here. And we know from the problem statement that this is going to be S equals to 0.5 meters. Okay, so however we solve this thing, we know that that's what it's going to look like. Okay, so we don't know this value up here, let's say, just yet. We know S is going to start at 0, and we don't exactly know the shape of that curve yet, although I've captured the curvature of it, I think, correctly. So what we've got here now is some expectation about what's going to happen. Let's go ahead and use the mathematics and actually use whatever equations are relevant to go ahead and see whether we've got this right or whether we've got this wrong. So step 1. Let's go ahead and write an equation for the velocity as a function of time. Okay, so we've got a couple of things to think about here. Let me go back to the original picture and we'll make some observations here. So we know that V equals 10 meters per second at t is 0.1 seconds. And we know V is equal to 0 meters per second at t is equal to 0.2 seconds. And so since these are linear on the graph, we figure that we need to know something about this slope right here, and that's what we're going to do next. So if we look at the slope of the V curve, we find out that it looks like this. There's time, there's V, comes up in a linear way up to there. This is 0.1 seconds, and this is 10 meters per second, so that the slope is really just equal to 10 meters per second divided by 0.1 seconds. So that's equal to 100 meters per second squared. And what this indicates is that V of t is just going to be equal to 100t. It's got units of meters per second, and that is valid for 0 t to 0.1 seconds. Okay, so that's our first equation. Now the question is, what happens after that? Well, there's a couple of ways to look at this. I'm going to write it one particular way. There are other ways you can write this as well. We know the slope on the other side of that, the post 0.1 second part of it, is going to be negative 100 because it goes back to 0. So V of t then is going to be V max, which is 10 minus 100 t minus 0.1. Again, that's going to be in meters per second, and that's going to be good from 0.1 to 0.2 seconds. So now that we've got our equations for V, which are valid over the entire domain, we can go ahead and move on to step 2, where we begin to construct the S versus t graph. So step 2. We're going to try and derive an equation for S as a function of time. So the way we usually do this is we write an equation which says V is ds dt, and then we kind of separate that. We say ds is equal to V dt. And so then we turn that into an integral, of course, which is an integral from 0 to S of ds. That ends up equaling a 0 to t integral of V dt. And so we have an equation for V. In fact, it's defined in 2 parts, so we can go ahead and piece together what we think the total displacement is going to be based on integrals of those 2 parts. So let's start with 0 to 0.1. The equation looks like this. S just turns out to be an integral from 0 to t of 100t dt. So that just equals to 50t squared. Okay, and we know from the problem statement that at t is equal to 0.1 seconds, we know s is equal to 0.5 meters. And indeed it is, if we plug in t is equal to 0.1 seconds. So that worked out okay for us. Let's go on to the next phase of this, and that is from 0.1 So let me write this integral without inserting the bounds of integration for a moment. On the left-hand side, we're going to get ds, and that's of course an integral over some bounds. On the right-hand side, we're going to get an integral of 10 minus 100 t minus 0.1 dt. Now let's talk about the bounds of integration. On the left-hand side, we know that at t equals to 0.1, we have s equals to 0.5, so that's the lower bound of integration. And then the upper bound of integration is whatever s maximum is, and so that's sort of what we're solving for. On the right-hand side, we know this goes from 0.1 up to t, and so I'm going to go ahead and keep that as an integral over t, and you'll see how this unfolds as we go along. Now you can make another choice here. You could put in a 0.2 and go ahead and do the integral, but I'm going to show you sort of symbolically how this turns out, and then we'll plug in t equals to 0.2 a little later. Okay, so let's go ahead and do this integral. On the left-hand side, we get s minus 0.5. On the right-hand side, it turns out to be 10t minus 50t squared plus 10t. That's all going to be evaluated from t down to 0.1. And so when we do this, we get s minus 0.5 equals to 20t minus 50t squared. And then we subtract off the values when we substitute in 0.1 for the time, and that turns out to be 2 minus 0.5. When we do all the math, we get s turns out to be equal to minus 50t squared plus 20t minus 1. Okay? And then at t is equal to 0.2 seconds, it turns out that s just turns out to be 1 meter. Okay, so if we go to a clean page here, now we can construct what the S curve is going to look like. So the ST graph is going to be something like this. Okay, so there's time. Here's S. Let me put up some dashed lines here. So there's 0.2 seconds. There's 0.1 second. We know we're going to have a point here at 0.5 meters, and the graph is just going to come up here somehow like that, and then over here, and this is going to be 1 meter. It's a nice smooth curve, a lot like the one we showed in step 0 when we had intuition. Let's go ahead and do step 3 now, where we write an equation for the acceleration, a as a function of time. Now this is a pretty easy one because we know that the velocity is a linear function of time, which means the acceleration is constant, and the acceleration is just the value of the slope of the v curve, as we described before. For 0 to t to 0.1, what we're going to get is the acceleration as a function of time is positive 100 meters per second squared. That was the slope of that first part of the curve. And then from 0.1 to 0.2, we get the acceleration is negative 100 meters per second squared. And so if we draw that, we're going to get something that looks like that. There's t, and there's a. Let me put up some dashed lines here. So this is 0.2 seconds. This is 0.1 seconds, and we can go ahead and say that this one is plus 100 meters per second squared. Over here we've got minus 100 meters per second squared, and it's sort of skew symmetric just the way we thought it was going to be back in step 0. So let's go back and review what we did. In this problem we had this particle moving through an electric field with a velocity profile which was linear. It was sort of a triangle wave. And the first thing we did that was useful is we developed some observations. We knew the shape of the velocity curve, and we know its relationship to both the s and the a curves, the position and acceleration curves. And so we were able to take a guess at what we thought was going to happen here. Then we went through and used some mathematics to go ahead and define the v curve, integrate to find the s curve, which we did here, and then differentiate to find the a curve, which we did here, and we found out that our intuition that we did back here in step 0 was indeed correct, and we had a second order position curve, a linear velocity curve, and then a constant acceleration curve. This problem asks us to consider general curvilinear motion of a particle. We've got a particle. It's traveling from A to B to C to D. And we know something about the geometry of those path segments that the particle is going to travel along. We also know something about the time it takes for the particle to travel along that path. So from A to B we have 2 seconds, B to C is 4 seconds, C to D is 3 seconds. And our goal here is to determine the average speed when this particle travels from A to D. So when we're talking about language like average speed, what we're really doing here is we're considering something like total distance traveled divided by total time that it takes to travel that distance. That being said, the approach is then pretty straightforward. So the first thing we want to do here is write out an average speed equation. Okay, and that average speed equation is going to be something like V average equals to the total path traveled, S total, divided by the total time, T total. And then in step 2, what we're going to do is we're really just going to focus on the thing in that equation that we don't know, and that is S total. And we're going to calculate S total using a scalar approach. Okay, so this is actually a reasonably straightforward problem. Let me make some observations about what we know first. You notice that here from B to C we know the length of the path is 15 meters, and then you notice that from A to B and from C to D are these quarter circle paths, and we know the radius of the circle in each of those cases. So really this is going to be a pretty straightforward way to go. Let me just go ahead and write step 1 right here on this page so you can see it. Step 1 is we're going to do average speed equation. Okay, we already know that that's going to include S total and T total, and so S total, just to be explicit about it, is going to be the path from A to B plus the path from B to C plus the path from C to D. And let me emphasize that this one from B to C we already know this is just equal to 15 meters. Okay, really, so the hard work in step 2 is confined to segments A, B, and C, D, and that's what we're going to do next. So step 2 is to calculate S total using scalars. Now I say they're using scalars as opposed to using vectors because the scalar approach is just much more convenient because we know that the geometry of the path is a circle. So let me go back to the picture here. And in blue, let me outline that path. So here's from A to B. So that is 1/4 of the circumference of a circle, and so that's going to be an easy enough thing to calculate. So let's go back over here and actually make that calculation for segment AB. We know we're going to get SAB is equal to the circumference of the circle. That's 2 times pi times the radius, and that's going to be divided by 4 because it's a quarter circle. So this is 2 times pi times 10 meters divided by 4. This turns out to be 5 pi meters. From C to D we can make the same kind of calculation. S from C to D is equal to 2 times pi times the radius on that segment divided by 4, and that's just 2 pi radius of 5 meters divided by 4. This turns out to be 5 pi over 2 meters. So we add that all up. S total is going to be 5 pi plus 15 meters plus 5 pi over 2 meters. Okay, so just to be clear here, this is segment AB, this is BC, that's CD. That all ends up, once we do the math, adding up to 38.56 meters, and that means if we use our average velocity equation, we get V average is equal to S total divided by the time total, so that's 38.56 meters divided by the total time. Let's go back to the problem statement. The total time is given by 2 seconds plus 4 seconds plus 3 seconds. That's 9 seconds is the total time as given in the problem statement. So that means we put 9 seconds down in the denominator there, and we end up with 4.28 meters per second. And there is your answer for the average velocity of the particle. Let's review what we did. So we have a particle traveling along a curved path, and our goal here is to determine the average speed. And the average speed equation is easy enough to come up with. It's the total length of the path traveled divided by the total time it takes to travel along that path. So the equation is pretty straightforward, and in this case, the hardest part of the problem was determining the path length from A to B and from C to D. Once we recognize that those are just quarter circles, we can go ahead and use our circle equations to figure out what those path lengths are and come up with the final solution for the average velocity, 4.28 meters per second. In this problem, we're going to consider a way that we can write acceleration using normal and tangential components. So we've got a jet plane. It's traveling along the parabolic path that is shown, and we actually know the equation that describes that path right there. When the jet is at point A, this point right here, we know that it has a speed of 200 meters per second, and we know that that speed is increasing at a rate of 0.8 meters per second squared. Our goal here is to determine the magnitude of acceleration of the plane when it is at point A. So because the plane is traveling on a curved path, a really useful way to look at the acceleration is using normal and tangential components. And when we're going to do a normal and tangential component of acceleration problem, we follow this typical kind of approach. So the place to start is by writing the acceleration equation. And we're going to do this in terms of normal and tangential components. Now, you've seen other ways to write acceleration equations and other kinematic type equations. We're going to use the normal and tangential components in this problem. Steps 2 and 3 then are going to work together. One of them is going to be to consider the tangential component, one for the normal component. I'm going to do the tangential component first. That's going to be step 2. And then in step 3, I'll go ahead and do the normal component. And finally, once we have those two components, we can go ahead in step 4 and find the magnitude. Now that magnitude calculation is going to be something like the square root of the sum of the squares of the normal and tangential component. While we have the figure up and before we start step 1, let me just go ahead and make sure that you understand what's going on with the problem statement. So if we look at the speed at point A, we know that that speed is 200 meters per second. Presumably that is in the direction of the nose of the aircraft, like that. So that's V at A is 200 meters per second. And we know that that speed is increasing at a certain rate. So draw another vector over here. And this is 0.8 meters per second squared. Now I'm intentionally not labeling that to say it's an acceleration or an acceleration in a particular direction. I just want to make sure that you get the point that that is in the same direction as this speed that we are given. What we're going to do in step 2 is sort of figure out what that 0.8 meters per second term really means. Okay, that said, let's go on and do step number 1, which is to write an acceleration equation. Okay, so in normal and tangential components, the acceleration at point A is going to be written as a tangential component and a normal component. And the notation we use here is the tangential part is v dot times a unit vector in the tangential direction. Then the normal part is a v squared over rho times a unit vector in the normal direction. Now we use these unit vectors to indicate the directions, and then the notation here is that v, of course, is the speed at any particular point, rho is the radius of curvature, and then v dot is the rate of change of speed. Okay, so you can probably sort of see the direction that this problem is going to go, and as we do steps 2 and 3, I think it'll become quite clear that this is a relatively straightforward thing to do. So let's do step 2, which is to consider the tangential component. So we're given the information in the problem statement that v dot at A is equal to 0.8 meters per second squared. And really what that means is that the acceleration in the tangential direction has a magnitude of 0.8 meters per second squared. And if we write that as a vector, that just is times a unit vector in the tangential direction. So in terms of the given information, that rate of change of speed, that really is just the tangential component of acceleration. So that was a pretty easy one to come up with. Here is our tangential component. Now step 3 requires a little bit more work, so let me go ahead and actually just start a new page here so you can see the whole thing. So step 3 is to do the normal component. Of acceleration. And in order to do that, you remember that the equation had both a velocity term, which we already know, it was 200 meters per second, and also had a radius of curvature term. So that's what we're going to focus on here. So the question is, what does that radius of curvature look like? Well, let's go back to the original figure and see if we can't make some sense of this. So let me use blue here, and you can see that the path that the plane is following at this instant is sort of got a slope to it like that, and the center of curvature of that path is going to be over here somewhere. Okay, because that's the sort of concave side of the path. And then the radius of curvature is going to be that distance right there. Now I have not necessarily drawn that to scale. I don't know exactly where that center of curvature is going to be, but this is the kind of calculation we're trying to make here. And in order to do that, in order to identify the radius of curvature, we need to know something about 1, the shape of the path, and 2, the position of point A. And so that is what's happening here in this radius of curvature calculation. Okay, now the way that we do that is using a radius of curvature equation, which you've probably seen before, both in this class and in calculus, and that looks like this. Radius of curvature rho, 1 plus dy dx, the quantity squared, and then all of that in the numerator, that's to the 3/2 power. And then this is divided by the second derivative, d squared y dx squared. Okay, so what we need here is to use that equation which describes the parabolic path and go ahead and do some derivatives and then see what we get. Okay, so I guess I should say that we're going to evaluate all of this at point A to get a numerical value for the radius of curvature. Alright, so let's go ahead and look at this. We know that the shape of the curve is y is equal to 0.4 x squared, and this actually has units of kilometers. So that means dy dx, that's going to be 0.8 times x, and then d squared y dx squared, that's just equal to 0.8. Okay, now what we need to do is evaluate these things at point A, and we know the coordinates x and y for point A, so this should be pretty easy to do. What we find out is that if we go back to the beginning here, A is at an x coordinate of 5 kilometers and a y coordinate of 10 kilometers. So if we go back to our equation, we're going to plug in x equals to 5 kilometers and see what we get. Okay, so let's do that on the next page. If we write this equation out, rho at x equals to 5 kilometers, we get 1 plus, and then 0.8 times 5 kilometers, that's 4. That's going to be squared, and then that numerator to the 3/2 power. Then the denominator is just going to be 0.8. That was a constant for the second derivative. And if we work that all out, we get 87.62 kilometers for our radius of curvature. Okay, so that was a pretty straightforward calculation, and in particular because the shape of the path was a polynomial, it was easy to go ahead and take the derivatives and figure that out. So what we can do then is we can write the acceleration, point A, in the normal direction, and this is going to be equal to v squared over rho times u in the normal direction. Okay, and then this is going to be written in terms of either meters or kilometers. Since I've got the radius of curvature in terms of kilometers, I'm going to go ahead and write the speed as 0.2, and just to be for emphasis here, we've got 0.2 kilometers per second. That's going to be squared divided by 87.62 kilometers UN. Okay. I could have easily written the radius of curvature in terms of meters just to make the units match up. And so the way this works out is we get this to be 0.456 meters per second squared, and that's going to be in the direction of the unit vector in the normal direction. Okay, so I've done the unit switch here just to be clear. I've gone from kilometers back to meters, and I did that because the tangential acceleration was expressed in meters per second. Okay, now one thing we haven't done yet is identified what the normal and the tangential directions actually are. We haven't identified those unit vectors just yet, but it turns out for this problem we actually don't need them, because what we want to do is we want to figure out what the magnitude of the acceleration is. So we're going to go on to step 4, and I'll show you how to do that. So step 4 is to make a magnitude calculation. So let me just go ahead and write the total acceleration at A. So this is 0.8 in the tangential direction plus 0.456 in the normal direction. That has units of meters per second squared. And so if we're going to take the magnitude of that, we're going to say the magnitude is going to be the square root of the sum of the squares of the components, because the normal and tangential directions are perpendicular to each other. So we can just write 0.8 squared plus 0.456 squared, square root, and we end up with the magnitude is equal to 0.921 meters per second squared, and there is your numerical value for the magnitude of the acceleration at A. Now if we were going to go ahead and figure out what those normal and tangential directions were and write the vector for the acceleration of A, we would look at the normal direction and tangential direction again in terms of that equation which describes the path of the plane. Now we're not going to do that now, but you could do that again by taking derivatives and identifying the location of the center of curvature, and then going ahead and figuring out what the directions of those unit vectors are. Let's review what we did. We had a plane flying on a curved path, and we wanted to express the acceleration of that jet in terms of normal and tangential components. So we started off by looking at the acceleration equation, which had the tangential and normal components listed, and it identified the key quantities we needed to know. So that was v dot, that's the tangential component, and then v squared over rho was the normal component. The tangential component, as it turns out, was given in the problem statement of this problem, so that was pretty easy to do. And then on the normal component, the hard work revolved around identifying the radius of curvature. And because our curved path was actually a polynomial, this was actually reasonably straightforward to do. We just had to make sure that we evaluate the radius of curvature at the correct location, that is, at point A. We can then write our normal acceleration at A, and then find the magnitude by taking the square root of the sum of the squares. So the magnitude of the acceleration of A, 0.921 meters per second squared. In this particle kinematics problem, we're going to look at motion along a helix and try to identify components of velocity and acceleration. We've got a boy sliding down a slide at a constant speed of 2 meters per second. So we've got a 2 meter per second speed as he moves down. Now the slide is in the shape of a helix, as you can see, and we're given some dimensions, for example this radial dimension, and also this dimension which indicates sort of the length of the helix. And we're also given some equations which talk about the relationship between z and theta. And our goal here is to determine the boy's angular velocity about the z-axis and the magnitude of the acceleration. Okay, so when we are doing this sort of thing, when we're looking at kinematics, we follow an approach that looks like this. So step one is, as it usually is, to define a coordinate system. Now, the keen observer will see that the problem statement sort of gives us a coordinate system here, but we'll talk about why that is a sensible coordinate system to use in step one. Step two, then, is to consider the velocity equations. And in particular, the relationship between z and theta. And then in step three, we'll look at the acceleration equations. And again, here we're going to focus on a magnitude calculation as it's asked for in the problem statement. Okay, so let's go ahead and do step one right here on this page and just talk about why the coordinate system that has been chosen for us is a decent choice. So step one, the coordinate system. Well, I think the best way to describe the coordinate system is that this is a coordinate system which is a cylindrical coordinate system, and it makes sense because of the shape and the geometry of this slide, which is a helix. So we've got r and theta pointing in a particular direction, then we've got the z coordinate up here, which is the right one, the one that's going to be most useful for us to describe that z direction. Now we know, again, the sort of lead of the helix is 2-meter spacing among the pieces of the helix, and we know that r and theta are going to be useful because the helix is actually sort of a circular path. So if I were standing up here, let's say above the slide, and I were looking down, it would essentially look like a circle. And so that's why this cylindrical coordinate system is a good choice for this. Okay, so now that we've got our coordinate system laid out, we can think about the velocity equations in step two. Okay, so step two, the velocity equations. Let's start with what we know. We know that the sort of radius, the circular radius of this helix is going to be r is equal to 1.5 meters. That is constant. And so the consequence of that is that r dot is equal to r double dot. That's just going to be equal to 0. So both the velocity and the acceleration terms, r dot and r double dot, are going to be 0. And you'll see how that cascades through the calculation as we move along. So we know something about r. Now the question is, what do we know about z and theta? Well, we're given some information in the problem statement that says z is equal to minus theta times pi. Divided by pi. Okay, and that's an interesting observation to make because as we go from, say, theta equals to 0 to 2 pi, that is, we make one sort of rotation around the outside of the helix, you can see that we are going down by 2 meters. So just to make that point, at theta equals to 2 pi, z is equal to minus 2 meters. And if we go back to the figure, that's this value right there. Okay, so you can make sense of why that equation is describing the situation. What that also allows us to do is to do some differentiation and figure out what z dot and z double dot are. So for example, z dot then just equals minus theta dot over pi, and z double dot just equals to minus theta double dot divided by pi. Okay, so now the question is, if we can figure out, either z dot or theta dot, or z double dot or theta double dot, then we can make some progress here on understanding all the velocity and acceleration kinematics. Okay, now one other thing that we know, and it's a little bit of a question how to use it, we know that v equals to 2 meters per second, and that is a constant. And the question is, how is v related to either one of those? That's the question we're trying to answer here. And we're going to answer it on the next page. So we know that the velocity, as given in the problem statement, that's really a resultant of whatever the velocity components are that we can describe for the problem. So let me go ahead and write an equation, and then I will explain a little bit about how we came up with that equation. So let's write a velocity equation that looks like this. The velocity is equal to the square root of the sum of the squares of the components of velocity, of which there will be 3. Now in cylindrical coordinates, those three components look like this. There is an r dot squared term. That's the first one. And then there is an r theta dot term. That's also squared, of course, because we're doing the square root of the sum of the squares. And then we're going to get a minus theta dot over pi term. That's going to be squared. And we're going to take the square root of the whole thing. Now let me explain where those terms come from. So this first one is really the r component of velocity. That's that one right there. This next one is the theta component, the so-called transverse component. That's right there. And then this last one is the z component. So that's the motion along the long axis of the helix. So if we were to write a velocity vector, it would include all three of those components. The magnitude of that velocity would then be the square root of the sum of the squares of those components. Okay, now we can make the observation that the r component here is 0 because we established that r dot is equal to 0. And so what we're left with is one unknown, theta dot, on the right-hand side. And we know from the problem statement that this velocity is constant and it is 2 meters per second. Okay, so now what we have to do is go back and sort of substitute in and see if we can't calculate what theta dot is going to be. Okay, so that calculation is going to look like this. 2 is equal to, and then r is 1.5, theta dot, that's the quantity squared, plus a minus theta dot over pi squared, square root. And when we go through and do some algebra, we get 4 is equal to 2.25 theta dot squared plus 1 over pi squared theta dot squared. And when we solve that, we get theta dot is equal to 1.30 radians per second. Okay, so that was a useful calculation to go through because now that we know theta dot, we can make some observations about what z dot is, and we can go through and do the acceleration part as well. Okay, so let's go ahead and think about that now. So step 3 is to look at the acceleration equations. Let's start with what we just looked at. We know that theta dot now is equal to 1.30 radians per second. We know that since the speed was constant at 2 meters per second, that means theta dot must be constant. And of course that just means then that theta double dot is equal to 0. Okay, we can then propagate that theta dot term in through the velocity equations and the acceleration equations as shown next. So the acceleration in the radial direction, AR, the fundamental equation there is r double dot minus r theta dot squared. This is going to be equal to 0 minus r, which is 1.5, and then 0.30 squared. So this turns out to be minus 2.55 meters per second squared. A in the theta direction is r theta double dot plus 2 r dot theta dot. R double dot was just 0. Excuse me, theta double dot was 0. And then to that we add 2 r dot theta dot. R dot was 0. So that just turns out to be 0. And that's going to be something like radians per second squared. And then A in the z direction is just z double dot. And that's going to be equal to minus theta double dot over pi. So that just equals to 0 meters per second squared. So there's your accelerations along this helical path, the components AR, A theta, and AZ. Now the magnitude then is just going to be the square root of the sum of the squares of those three components, and as you can see, only one of those components is non-zero. So what that means is that the magnitude of the acceleration is just going to be equal to the magnitude of that one non-zero component. That's just 2.55 meters per second squared. And there is your answer for the magnitude of the acceleration. Let's go back to the beginning and look at what we did. So we had a boy traveling down a slide on this helical path, and our goal here was to figure out the angular velocity about the z-axis, that's theta dot, and the magnitude of the acceleration. So the first thing we did was look at a coordinate system that was actually defined for us in this problem. So then we went on to these velocity equations that you see here. R turned out to be a constant along this helical path, and then we derived a relationship between z and theta and the derivatives of z and theta. The important part of this problem was the recognition that the velocity is constant, and that velocity is really the resultant of the square root of the sum of the squares of the three components of velocity, the r component, the theta component, and the z component. And we were able to go ahead and solve for that angular velocity that was asked for in the problem statement here by relating it back to the constant speed that the boy is traveling. Once we knew that, we were able to go on to the acceleration equations, and several of the acceleration components fell out of the equation. They turned out to be 0, and the magnitude of the acceleration just turned out to be 2.55 meters per second squared. In this problem, we've got a roller coaster ride of height h. And the idea here is that we want the car to start at A, at the top of the hill, at rest, and we want to design this roller coaster such that the car reaches a speed of 100 kilometers per hour when it gets to the bottom down at point B. We also want to shape the track at point B with a radius of curvature rho such that the passengers do not experience a normal force greater than 4 times mg. So these roller coaster problems are kind of classical dynamics problems. We've got a car that's going to start up here at rest, come down here to B, and achieve a certain speed, and we also want to control the acceleration. And so these are great work energy type problems. So our approach is going to look like this. Step 1 is to state a work energy relation. And one of the things we're going to have to do here is establish a datum from which we're going to measure our work. And from here, we're going to be able to actually solve for h. And then in step 2, we have to calculate rho for the normal force constraint. Okay, and this is actually going to be the kinetics part of the problem that's going to involve a free body diagram, as you're going to see. Now, before I go on to step 1, let me just go ahead and give you some guidance on how to establish the datum that we were talking about before. It's sensible to establish the datum out here at point B. Okay? And then we can measure h relative to that. So what we're really looking at here is the amount of potential energy that is a function of the elevation above point B. That is, it's just going to be a function of h. Okay, so we're going to go on to step 1 and show you how that looks. Okay, so step 1 is we're going to state the work energy relation. Okay, so the sort of basic equation is that the energy, the kinetic energy at A, plus the work from A to B is going to be equal to this kinetic energy at B. And just to remind you, we have this sort of shape like this. We have A up here and B down here. This is our datum. And this is going to be a height h. We have the car starting at rest up here at A, so we would say the kinetic part up there is going to be 0, and then the potential part down here at B is going to be 0 as well. So the work that is done is really sort of trading all the potential energy at A, trading that in for kinetic energy at B. Okay, and so the way this is going to go is that TA is going to be equal to 0, so we will just sort of scratch that out of the equation. Then the question is, how do we characterize the other terms in the equation? Well, we know TB is going to be something like 1/2 m velocity at B squared, and we know the velocity at B is supposed to be 100 kilometers per hour, and if we want to do a units conversion there, we would do times 1 hour is 3,600 seconds, and then we would put 1,000 meters per 1 kilometer. And so this turns out to be 27.78 meters per second, okay, once we do the conversion. And we know that our work is really just going to be equal to the potential energy at A that we are exchanging. And so we can characterize that as just mgh. Okay, so this is going to be the mass of the car plus the riders times our gravitational acceleration times h. And so what we're going to do is we're really just going to equate these two terms right here, this one and this one, and we're going to see what we get. So let me go to a new page and do that. So the equation turns out to be TA, which we know is 0, plus the work, which is m times 9.81 times h. That's going to be equal to 1/2 m times the velocity at b, that's 27.78, and that is squared. And so when we cancel the m's, the masses, from each side, we can just calculate h turns out to be 39.32 meters. Okay, so there's our h. That is the h that gives us enough potential energy all the way up at the top of the hill at A that we can trade all that potential energy in for kinetic energy at B and get up to the speed that we really want to achieve. Now the question is, what does the acceleration relationship look like at B? And so that's what's going to happen here in step 2. So step 2 is to calculate the radius of curvature rho for the normal force constraint. So this is a kinetics type problem, so let me write the free body diagram over here to the side a little bit, and we're going to write this exactly at point B. So here is the car. It's got some wheels on the bottom. Now we're going to consider this thing to be a particle, so we're not going to consider the size or the distribution of mass. We're just going to give it a single mass, which is m times g, that's the weight. And then up here we have the normal component of acceleration, and this is really just going to be 4 mg. Okay, so if we had a coordinate system like x and y, then we can go ahead and write a sum of the forces in the y direction equation that would look like this. It would be 4mg minus mg, and that's going to be equal to the normal direction acceleration times the mass, so that's going to be m times velocity of b squared over rho. Okay, so you can see how this is going to turn out. We can go ahead and cancel the m's from this equation. So there's an m and an m and an m. And on the left-hand side, we get 4g minus g. So that's 39.24. That's 4g minus g, 9.81. And that's going to be equal to the velocity squared divided by the radius of curvature rho. And so if we go ahead and do the algebra and solve that, we end up with the radius of curvature just has to be 26.22 meters. So the kinetics part of that was easy enough to work out, and we solved for the required radius of curvature to control the normal component of acceleration. Okay, let's go ahead and review what we did. These roller coaster problems are always classical ways to introduce various kinds of concepts. Here we're looking at work-energy relationships. And first we had to figure out what the height of this hill was to achieve a certain velocity at the bottom of the hill. And so we wrote a work-energy relationship that looked like this. And essentially what we were doing is taking all the potential energy up here at A and turning it into kinetic energy down here at B. And that was an easy enough thing to do, and we solved for the height of about 39 meters. Then the kinetics part of this was the normal force constraint, where we had to draw a free body diagram and limit the normal force. And when we did that, and we equated that to the acceleration in the normal direction times the mass, we found out that we could isolate the radius of curvature and solve for the required radius of curvature a little over 26 meters.